Hi everyone, Phil from statisticsmentor.com. So, you know or you've been told that you have to fit a regression model. So just what can a regression model do for you? Let's start first by talking about what constitutes a regression model. In a regression model we have two types of variables. A dependent variable, that is the one we wish to use the model to explain, and the independent variable. Generic symbols, y to denote the dependent variable and x to denote the independent variable. And as the name suggests then, dv, the dependent variable, depends or is explained by other variables. Hence this x here is the independent variables. Now there's some other jargon which mean the same thing. So response variable also means the dependent variable. Instead of using the word independent variables, you'll see some text using the word predictor or explanatory variable, or I've missed another one out, covariate. Covariate. Sorry, I don't have my pen with me, so covariate. Okay. Now, once we have the regression model, we can use it to do two things, and it's important to bear this in mind because it keeps your head kind of focused on what you're trying to use the model for. You can use the regression model to make predictions about the values of y given the values of x. So in other words, suppose you've got you're thinking about a scenario. So x takes a particular value. What predicted value does the model have for y? Okay. Now the word prediction here is not to be confused with cause and effect. We can't say that x causes y, although a regression model could be part of the evidence for a cause and effect relationship. Prediction is the word prediction means something else. It means that given the value of x, the model, what does the model say, guess about the value of y? It doesn't imply that x causes y. Okay. The other thing we can use the regression model for is to say things like, if x increases by 1 unit, the model predicts that y will increase by blah 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 units. For example, in marketing, x could be amount spent on advertising, y could be sales. So we could make the statement with regression such as, if we spend an extra £1,000 on the marketing campaign, the model predicts that sales will, which is the y, will increase by maybe £8,000 per week, something like that. Okay, so bear in mind that once we've got the regression, we can use it for prediction. Given values of x, we can say the model can predict the actual value for y, or we can use it to measure the sensitivity of the y to x using a sentence such as, if x increases by 1 unit, the model predicts that y will increase or decrease by so many units. Okay. Now in the first course in stats, the first regression model you will be introduced to is the simplest one of all. It's called the simple linear regression, or the bivariate regression, because there are two variables. It's just the one dependent variable and the one independent variable. In any model there's always only going to be one dependent variable. There can be one or more independent variables. In a model where there's only one independent variable, we call that model the simple linear regression model. Where we have more than one independent variable, we have what we call the multiple linear regression model. Okay, so now let's turn our attention to examples. I'll show you how to get the output for the simple linear regression model given data, and also have a brief look at the output. So I have two variables, y and x, and moreover they are, the y is scale. It is not categorical. Alright, this is important because in regression, first of all, before you can run it, you've got to look at your y. Is it continuous as scale? If it is, we can run the standard regression model. If it isn't, we can still run a regression, but then it's going to be a non-standard one, and it's slightly more technical. Alright, so the first regression model you ever look at, and of course, will be one for which the y, the dependent variable, will be on the continuous scale. The x here is also on the continuous scale, but notice that there's no such restriction on x. X could be qualitative, or x could be, if you've got more than one type of independent model in your model, you could have a mix of continuous and non-continuous. Right then, to fit this simple linear regression model, go to Analyze, Regression, Linear. Here the box pops up. Okay, it should all be empty in these options boxes. Dependent, so we transfer our dependent variable into that using the arrow, or you could just type it in, but let's use that. Notice the ruler here denotes that it is scale variable, so it's fine. Independent variable, our IV is just the x, so we transfer that in. Now there are various options here, but we're just not going to look at those. We're going to just look at the bog standard output. So click OK. Right. So let's just have an overview of what tables we're given. We're given one table, two tables, three tables, four tables. Right, there's a heck of a lot of output. The first one doesn't tell us anything, just tells us what x is in the model. Model summary. Now, we're interested here in the R and the R square for simple linear regression. R is actually here in a simple linear regression. R is the correlation coefficient. So we call it a correlation coefficient, takes the value from -1 to +1. Closer is to either -1 or to +1. That means the stronger the negative or positive linear relationship between the two quantitative variables. Here it's 0.599, that is over 0.5, so you could say there is, and moreover it's a positive sign or negative, so we can say that's a positive correlation between y and x, and that could be moderately strong. One has to be careful about talking about the strengths of relationships, because with real data depend on your subject field you're studying. In some subjects around 0.3 could be moderate, and some subjects 0.3 could be considered quite strong. Okay, the R square, not to be confused with R. So R square is otherwise known as the coefficient of determination, takes the scale of 0 to +1, and closer is to 1, that means closer the line is to all the dots. In the case that R square is equal to 1, it means you've got a perfect fit, because the model will explain precisely about the relationship between y and x. In other words, the line passes through all the dots, which in real life data will probably not be the case. So here the R square is 0.36 or 36%. We could say that 36% of the total variability in the dependent variable is explained by the model. I'll say it again. We can report, if we have to write this down, that R square equals 0.359 means that approximately 36% of the total variability in the DV is explained by the IV, or the model. Now, in regression, there are two basic tests that are presented in the output. You have an F-test, which is here under the ANOVA table, and we also have a T-test. Okay, recall that for any test, since we're doing applied stats, for any test we just need to know what is the null and what's the alternative experimental hypothesis for that test, and then we just interpret the corresponding p-value. denoted in SPSS by sig. Alright, for the F-test here, the null hypothesis always, for the ANOVA table in regression, the null hypothesis is that the model has no explanatory power. Another way of putting that is that the IVs in the model do not help to predict why. Yet another way to say that is there is no relationship between any of the IVs to the DV. Okay, pick whichever one of those statements I made makes sense to you. Okay, so the value is 5.6. What is the but that value is not of interest in itself, but if you were to report it, you just write that down. We're actually interested in the sig, the p-value. 0.039. That is less than, if we're going to use the standard yardstick 0.05, it's less than that, so it means that we reject the null in favor of the alternative. Conclude that there is some explanatory power in the model. In other words, the IV, there's evidence that the IV helps to predict the DV. Alright? Okay. Now many students, it's quite common that students forget this rule about the p-value, but it's easy to remember. Just remember, if p is low, null must go. So what do we mean by low? We could say that's 0.05 as the threshold, so lower than 0.05 means null must go, i.e. reject the null in favor of the alternative. Next, we come on to the coefficients box, probably the most interesting of the boxes. We're going to look here at a t in a moment, but first let's look at the actual model here. Unstandardized coefficients, that's the betas down here, constant, that is for the intercept, x, that is my IV, and these are the coefficients. Now if I were to write this down as a formula, because this is ultimately what I'm interested in, because these coefficients here will help me to get my predicted values of y given x, and also it'll help explain to me what happens if x increases by 1 unit, what's the impact on y. So we can see all that if we write this down as an equation. Okay, so we can write this as, and I'm not going to be too pedantic here, y equals 156, which is the intercept, right? Just I'm looking down this column here, these are the unstandardized coefficients to be, plus 0.338 times x. That is the model. And then this is the formula of a straight line where the intercept, the y-intercept is 156 and the slope is positive, so it's an upward slope curve, 0.338x. Okay, that's what we can see from here. Now at this point we look at the significance level, the t statistic. Okay, so it's a test, so what's the null hypothesis? Okay, for this default output, the null hypothesis is that the coefficient in question, notice there are two t's here, one for each row, one for each of the parameters. So the null hypothesis is that the coefficient in question is equal to 0 versus the alternative experimental hypothesis that the coefficient is not 0. Another way of expressing this is the null is that the coefficient is insignificant and the alternative is that it is significant. Again, we just need to look at the p-values to determine whether we go with the null or the alternative. Now we're not too bothered about the constants. We're always interested for sure in the coefficient on the IV, otherwise known as slope coefficients. Okay, so the t statistic for the x is 2.368. The associated p-value is 0.039, which is less than 0.05. So using the rule that if p is low, no must go, we reject the null. Conclude therefore that the slope coefficient here is not 0, it is significant. Okay, it's significant. What does that mean? That means basically there is a relationship, there's evidence of a relationship between x and y, which means that we can go ahead and start doing predictions or interpretations, subject to a massive caveat, which is that I'll tell you in a moment. It's not right to say at this point. Okay, so there we go. So this is our model. We found that it's significantly different from 0. So now we can use it for the purposes that we built it for, which is to talk about the relationship between y and x, or use it for prediction. Let's just give you a demo of what I mean by prediction. So prediction means that give me a situation where I'm interested in the value of x. Say x is 2. Does the model predict the value of y to be according to my model? Actually, yeah. Let's use this advertising and sale. No, let's not use advertising. So let's just do that. So y equals 156 plus 0.338 times 2. The model predicts that the y will be, get out your calculator, it will be 156 plus 0.338 times 2 equals 156.7 approximately. So that is the predicted value, 156.7 units, whatever those units of measurement are for y. Okay. What's the interpretation of this slope coefficient, which is another of the usages of a regression model? If x increases by 1 unit, the model predicts that y increases, because it's a plus on the it's plus on the coefficient on the slope, increases by 0.338 units. Here we replace the words units by whatever the measurement of x and y are. So if we're using sales, x is measured in £1,000, and we would say if x increases by £1,000, the model predicts that that's y. Say sales is measured in £1,000 as well, then the sales increases by £338 per period that we're interested in. Right, so to finish off, I've just got a few things to say. First of all, so we've said what the use of regression is. It is for making predictions. Given value of the independent variables, we can predict the value of y. We can use it to measure sensitivity of changes in y to unit changes in x. But we can only do that. That analysis that those statements that I've just made is conditioned on this model being the right model. All right. Now, how do we know that this model is an acceptable model? Well, the model is acceptable if two things really. If A, the statistical assumptions for regression are satisfied. These statistical assumptions are called the classical assumptions of regression, also known as the Gauss-Markov theorem. Okay, and this is where part of it is where if you want to check whether those assumptions hold, this is where we start looking at what they call the residual analysis. Okay, which is a big part of checking whether the assumptions hold. So residual analysis. So before we actually start making what I've said, statements about relationship between x and y using the model, we should have checked whether those assumptions hold. So we should have done a residual analysis, at least done a residual analysis. Okay, but that for a newbie like us, that we leave that to another time. Right, that's very important, that. Okay. Another thing is, in some courses they will show you, they'll talk about the standardized coefficients, because notice that there are actually two sets of coefficients, unstandardized and the standardized. Now there isn't one for the constant, there is one for the intercept. The standardized coefficients basically just alters the units of measurement. So whereas in the first example I gave you about marketing, about £1,000 increase in advertising for the X leads to a £338 increase in sales per week, say. So X and Y here both measured in thousands of pounds, but sometimes X and Y could be measured in different units. X might be kilograms and Y could be something like yes, pounds and pence or dollars or something like that, different units. By standardizing it, but the units of measurement for X and Y become standard deviations. So if we were to write down the model based on standardized coefficients, we would say for one standard deviation increase in X, the model predicts that the Y will increase by about 0.6 standard deviations. Okay, why would they want to do that? Well, if things have the same units, it might make it easier to understand. Okay. Finally, I'm going to finish off just by trying to link up some of these results in the tables together to make you kind of tie up some ideas here. Now, so this final part of the video, you might kind of watch it another time. Okay, I want to point out two things. Let's do the more important thing first. F-test, T-test. Right, I want to point out this stage that there are many F-tests and there are many T-tests. By many, I mean that these F-tests and T-tests do not have the same null and the alternative. So this F-test I said, the ANOVA table, means that the null is that the model has no exponential power. It doesn't mean that every single F-test you're going to see in your career in statistics will be testing that the model has no exponential power. Why these such tests are called F-tests is because test is based on looking up the critical value in the F table of F distribution. Likewise, the T-test is called T-test because there are many such T-tests, but all these T-tests are called T-tests because you need to look up the table of the T distribution to find the critical values. Alright, so don't think that you just memorize it once and then it's always going to be the same. However, for the regression in the default, the F will always mean the null always means that the model has no exponential power, and T is testing for the significance. Right, I want to say that the F, if you think about it, the null for the F here is actually the same as the null for the T. In other words, for the simple regression model, they're both saying the same thing, they're identical. Because what does F say? To think about what I said before, one way to express the null or the F is that the IV does not help predict Y. What that's same as saying? Must be same as saying the coefficient on the IV is 0. But that's what the T-test is testing for down here. And that's why it's not a surprise if you look at the significance level, 0.039, look at the significance for the F. Same, isn't it? Moreover, let's get out my calculator. Look what happens if I take the T for the slope parameter, 2.368, and I square it. I get 5.60. Look at that. It's the same. In other words, the relationship between T and F is quite clear. T square is equal to F. They're telling us the same, they're doing the same thing. But this is only for simple linear regression. Once you start doing multiple, don't think that this won't hold what I'm saying. Okay, so that's a bit of trivia. It might kind of seem to be a bit magic to you. Right, finally, there's also a relationship, and this could be an exam type question if you're studying this thing for college. There is a relationship between the correlation and R-square as well. Now, let's take the correlation, which is 0.599, and we square it. Look what we get, 0.359 if we round it up. Look at the R-square, 0.359. In other words, the correlation square equals R square. And this bit of trivia, this only holds for the simple linear regression model, i.e. one for which there is one IV. Okay, so the first remark I've made ties up the F with the T, so it ties up the results of these two tables. And in the model summary, we've tied up the relationship between R and R square. And these things I mentioned hold only for the simple linear regression model. So to recap, use of the regression model is to say something about the relationship between X and Y, which is stronger kind of statements than correlation can make. But these statements can only be made if the model is adequate. But adequate means that we should check that the conditions of the assumptions of regression hold, and part of this require using residual analysis. Okay, but that's for another time, and that's where it gets pretty messy. That's why statistics ain't so simple. Okay, well, get some data and have a go of that, and best way is to practice. Okay, good luck.